right, so now that we have battled some internet issues this morning, let's go and take on something that some of you have a little bit of experience with, maybe in science class at school, and maybe some of you have more experience learning about planets and planetary systems. And something as simple as the topic of our sun. The sun is, when you ask someone, okay, the sun, they'll tell you, oh yes, it provides light and energy and warmth to our planet, and even to planets out beyond ours. That's very true. But today we're going to make you little experts about the sun. You're going to learn some things about the sun that you may not even know, and how it works, and why does it give it this bright glow. And why does it even look like this? Here is an example of a great picture of the sun taken by some telescopes that we've created. And you're going to meet some of those telescopes at the end of the presentation also. They have done such a fabulous job in the technology, NASA and other private companies that have been able to capture the history of the sun and evidence of the sun that's ongoing, that's constant. And I'm going to tell you right now and put this to rest. The sun isn't going to explode anytime soon. It's going to be a while, and you'll find out why. Okay, so I'm excited. I hope you are excited. And let's begin this adventure of our sun. All right, and here we go. So what are we going to cover today in this webinar? Well, first of all, where is the sun? We all should know that it kind of is in the middle. It's a star, and there are planets that go around the sun. Now, how that works and how that was formed billions and billions of years ago is something I'm going to help you discover today. What is the sun? What is the sun? I mentioned it's a star. What kind of star? How long has it been around? Parts of the sun. There are parts in the sun from the very center all the way out to its outer layers that we're going to talk about today. How is the star born? We'll talk about nebula, protostar, a main sequence star, and we'll talk about this disk, this protoplanetary disk, kind of like the birth of our solar system. Are there other types of stars that exist? Absolutely. When you look up into the night sky, you're going to see different colors of stars. They might be sparkling white. They might be red or blue. We'll talk about those colors of stars. A star life cycle. We're actually going to take a little field trip through a nebula. So we're going to see the beginnings of a star or stars. How do we study the sun? What's out there that helps us understand the sun, this beautiful sphere of light, of energy, of heat? And then the northern lights. I'm sure some of you guys have heard of the northern lights. Why are they the color that they are? How can they be dangerous to our Earth? How is the sun dangerous to our Earth? We'll talk about that also. And I really encourage you after the webinar to have your big universe, go to your big universe and open it up and find some of these books on the sun, to do further research, to look at pictures. It never stops with the webinar. Your research continues, okay? All right, so let's begin with where is the sun? So as you notice from here, we talked a little bit before, the sun is at the center of our solar system. Now, it used to be thought back in ancient times that the sun would go around the planet somehow, okay? And they also thought this, our Earth was flat, but we know these two things aren't true. The sun is the star, and how do we find other planets like exoplanets? We look for the star, and there are ways to see if there's a star present. And also if there are planets that go around the sun, the star. So it's found at the center of our solar system, and we all know the inner planets, right? Mercury, Venus, Earth, and Mars. And those first 4 planets are very different from each other. They're the ones closest to the sun, but yet they're so different from each other. Venus is definitely different from Earth. I think Earth and Mars are probably the same. right? Pretty much they can be. Mars has been found evidence of liquid ice. Possibly it's got canyons. So it may have had some, like a Grand Canyon on Earth. It may have had a Grand Canyon on Mars a long time ago. From the inner planets, we have the asteroid belt. A lot of asteroids that are just floating out in space, held out there by gravity. The outer planets, the gas giants, Jupiter, Saturn, Neptune, Uranus, and even Pluto. If you believe like me, it's still a planet, but it's a dwarf planet. So this is the system that can be forming all the time in our galaxy because of a star, because of a sun. So we're going to watch a video here. It's called All About the Sun. So if you have paper and pencil, or if you have your phone, take some notes. And you can go back and study those notes. Here we go. So I'm going to come down my internet here. I've got it all ready to go. All right, and make sure you have your volume on. Let me turn mine on so that way you can hear it. All right, and enjoy, okay? I'm going to talk a little bit about some things in the video, so just be wary.
It rises in the morning, giving light to the land below it. It sets in the evening, leaving the world in darkness. It even provides the heat and energy necessary for life to survive on Earth. You know what I'm talking about, the sun. Because it is so important to us, the sun has been studied and observed since ancient times. Astronomers today still study it and are constantly learning new things about the sun, the center of the solar system. The sun is a star, not so different from the stars that can be seen in the night sky. It may look different, but that is because the sun is many times closer to us than any other star, which allows us to see how hot and bright it is. The sun may be close to us compared to other stars, but it is still very far from the Earth, about 93 million miles or 150 million kilometers away. Although the sun is so far away, it only takes sunlight about 8 minutes to reach the Earth because light travels so fast. Because the sun is so far away, however, it seems much smaller than it really is, more than 100 times the width of the Earth. The sun is so large that if it were empty, more than 1 million Earths could fit inside. The sun is the largest object in the solar system. In fact, if you collected everything in the solar system, including the sun, the planets and dwarf planets, comets, asteroids, and moons, the sun would account for more than 99% of it, with everything else adding up to less than 1% of the solar system. As far as stars go, however, the sun is average or even small in size. It is called a yellow dwarf, and there are billions of stars like it in the Milky Way. Like other stars, the sun is made of gases, mostly hydrogen, with a little helium, and only traces of other elements. These gases are held together by the sun's gravity, which creates such intense heat and pressure that it causes nuclear fusion, a process in which hydrogen atoms fuse to create helium at its core. The sun's core is about 27 million degrees Fahrenheit or 15 million degrees Celsius. By the time heat from the sun's core reaches its surface, temperatures have dropped considerably. The surface of the sun is only about 10,000 degrees Fahrenheit or 5,500 degrees Celsius. Unlike the Earth, the sun does not have a solid surface. You may be surprised to learn that the sun's gassy surface is not calm and quiet. Instead, the sun is constantly moving and changing, with sunspots, or dark patches of cooler temperatures, and solar flares, or eruptions of high-energy radiation, frequently marking its surface. All of the planets in the solar system, including the Earth, orbit around the Sun. In turn, the solar system orbits around the center of the galaxy in which we live, the Milky Way. It only takes the Earth 1 year to complete an orbit around the Sun, but scientists estimate that it will take the Sun about 230 million years to complete an orbit of the galaxy. Since ancient times, humans have understood how important the Sun is for life on Earth. Without the energy provided by the Sun's radiation, the Earth would be dark, cold, and uninhabitable. Although it has been studied for thousands of years, there is still much to learn about the Sun. I hope you enjoyed learning about the Sun, the center of our solar system.
So from that video alone, boys and girls, there is so much information that you may or may not have known about our sun. It's a beautiful structure, well put together, and we're going to kind of take it apart now. We're going to take apart our sun for a more in-depth understanding. So where is the sun? We already know, the center of our solar system, planets going around it. Okay, now let's look at the next part, which is what is the sun? So what is this fantastic sphere? Well, first of all, if you did hear me within the video time, we actually talked about how it's 93 million miles away from the Earth. And if you recall, it's only 8 minutes that light that travels to the Earth. It takes 8 minutes to do that, which is a fantastic understanding of how quickly that light travels through our solar system. Our sun gives us heat, light, energy. I know when I open my blind early in the morning, and it's still dark right now, but once it comes out, your body feels refreshed. You open up the blinds, open up the curtains, and you feel that energy just going right through your body. It wakes you up, right? And it is our brightest and closest star to us. The sun is only a medium-sized star, known as a yellow dwarf. The bigger the star, remember this, the bigger the star, the less life that it has. The medium-sized stars and even the smaller stars will tend to last a lot longer because of the way it is able to focus its energy inside. The Earth could actually fit into our sun about 1 million times. Our little Earth inside our medium-sized star 1 million times. It's crazy to think about. So the question is, what color is the sun? What do you guys think? So you think it might be white, and you're right. When we see it as orange and red and yellow, like, you know, when little kids color their picture of the sun, that's what we color it, red, orange, and yellow. Why do we color it that color when it's really white? Well, we have that atmosphere around our Earth that protects us from the sun, so we don't have that much radiation. And that atmosphere around our Earth is actually what makes our sun look yellow, orange, or red. It's that distortion of our atmosphere. So that's why, but it's really white. And when you look at the pictures here, you got to think about what is actually taking these pictures. What's capturing these images? Telescopes. And telescopes also have a protective kind of a visor, if you will, over the telescope so it doesn't burn up. So that protective visor can also turn and distort color. The electromagnetic spectrum is also come into play with different kinds of technology that's capturing images and video of our sun. So in the video, it did talk about the inner parts of the sun. What is this sun made of? Well, our Earth is solid in the middle. It's got a solid core. On the outside, you start to get some liquid heat, right? It's a liquid, it's a solid core and then a liquid. And that mixture together causes magnetism. within our Earth's core. And that's where you get your volcanoes, even the Yellowstone National Park, the geysers, the sulfur springs, and they burst up through the cracks of the Earth. So geysers and volcanoes are all because of our Earth, the magnetism that it's caused. Our magnetism, of course, goes from north to south pole, which is why our planet is spherical, not flat, because the magnetism pulls our planet apart. Well, we have a lot of different gases in our atmosphere and on our Earth: oxygen, carbon dioxide, nitrogen. We have methane gas. We have a lot of different gases. So they also play on the Earth, and the colors. Okay, blue is the ocean. You've got green for the, for all of the life that lives on Earth. However, the sun is not like that. It has magnetism, and a lot of it is because of the nuclear fusion. Remember in the video, it says it's mostly made of hydrogen, gas, and then helium. But then there's also trace amounts of different gases. But hydrogen and helium are the ones that are making up the sun. It does not have a solid core like the Earth. It's liquid all the way through, and it's gassy. It's very radioactive. Convection is a play on each other as far as the neutrons, protons go, which are the smallest elements of life. Here you see the photosphere, which is what you see in telescope pictures. How are these sunspots made? Well, that's magnetism. It actually closes on those sunspots. You're going to see some images with different colors that we've captured from electromagnetic spectrum. And it's going to be green and pink and red and these different colors that shoot out from the sun that cause solar flares or coronal mass injections or CMEs. So those ones, that's what comes to the Earth. Okay, those solar flares burst out from the sun at different times, and that causes damage to our Earth and to our communication systems. Can you imagine losing communication right now on the Earth with all the internet and all of the technology that we have? Oh boy, that would be a big problem. So given the structure internally of our sun, this is what is causing our sun to continue to stay its medium shape. It'll grow slowly, but also because of the nuclear fusion and the gravity. So let's take a look at what's called solar fusion on a video here to give you a really good idea of how the sun is working constantly. All right.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse, and that's very, very rare.
To force protons together takes immense amounts of heat and pressure, generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
But with gravity crushing things down, things get close enough together and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
So as amazing as our sun is, I mean, you're looking at the relationships with these protons and whether or not they're going to come together. It's a chance happening, but it happens a lot, actually. And that nuclear fusion is, again, that hydrogen, that helium, always constantly reacting with each other, but it's also the gravity, okay? The gravity is what's pushing down, causing that pressure. So here is a good example of what I just mentioned. So nuclear fusion, this is what causes our sun to have these sunspots, these solar flares, and of course, idea of magnetism. You've got hydrogen plus your helium plus your gravity. And I put that in big letters because it's the big force. It actually keeps our planets going around the sun and the sun doing what it needs to do. The sun formation, and it changes every second. So your cores, again, liquid. You've got pressure being pushed out because of nuclear fusion. You've got heat being pressed out, because from those pictures and video, you see like a fire. It looks like a fire, right? Well, that right there is you seeing nuclear fusion. Now, you're going to have all these explosions, and yes, gravity's pushing it down so it doesn't go and explode, which is where I told you the sun isn't going to explode anytime soon, okay? Because these forces are working against each other and gravity pushing down, okay? Keeping that sun in that nice spherical shape like you have our Earth, okay? Pushing down, but every once in a while, you're going to have something escape, that solar flare is escaping. That's where it's uncontrollable to some point, okay?
The sun is a beautifully magnetically driven star, but we can't actually see magnetic field lines. They're essentially invisible, and so we have to turn to models in order for us to see the global magnetic structure of the sun. What we're looking at here is one such model, and the color coding represents what we call open magnetic field lines, which means that they extend from within the sun all the way out to really, really far out in space. The green and the purple have a north and a south polarity. The white lines are closed magnetic field lines, so they come out from the surface of the sun and then they loop around and close near the solar surface. Now you can see how beautifully dynamic the sun is as well. Magnetic field lines interact with each other. They cause big explosions to occur on the sun, and that's one reason it's extremely important to study the magnetic structure of the sun, especially on a global scale. And again, models are the one way we can do this because they allow us to model where the field lines are, how they're going to interact with each other when the sun rotates, and then how that causes solar storms like coronal mass ejections and solar flares. Sometimes the sun is quiet, sometimes the magnetic field lines aren't doing a whole lot, but other times you see these bright regions on the sun where you have closed loops, and that's where activity can occur, where the flares can occur. So everything is really magnetically connected.
Okay, so you notice from this imagery, and again, this could be a variety of telescopes capturing this imagery through electromagnetic spectrum, which is where you get the various different colors. So if you notice the black spots are the sunspots, and if you notice the loopings, these kind of white loopings, they start within the core, rise to the photosphere of the sun, and then it goes back again, and it goes back again, and you have them all over the sun, sporadic, which means different times. Causing this nuclear fusion. Now, remember I told you that this heat and this light, this pressure is contained for the most part, but then you've got your little troublemakers, the solar flares. You see the pink colors, and these ones are also caused by magnetism, but they're escaping the surface of the sun, and they can go for quite a ways out into our solar system. And a lot of what you see on our Earth is what's called the northern lights. So at the North Pole and the South Pole, you'll see some of that activity, and we'll see some beautiful video of it here at the end, the different colors. Now, the different colors are caused by the gases of our Earth, Okay, remember I told you carbon dioxide, oxygen, methane, nitrogen is all present in our atmosphere. And that is what turns the solar flare activity that reaches the Earth from the sun. It causes it to be different colors, are the gases. But this kind of solar flare activity can be very dangerous. And it happens more often than we think, which is why we have to make sure we are always studying and looking at the sun, because back in the 1880, they had communications all over the Earth went out. It was dark. If you look from the International Space Station, you see lights on. Even at night, you'll see them. It's beautiful. But if you have solar flare activity, it can knock your communications out. Those lights that you see on the Earth are going to be black. Communications, and it's like billions and billions of dollars to actually change that. And that was back in 1880. Can you imagine in 2020, right now in 2020, what would happen to our systems? That would be a very scary thing. So now let's go into how a star is born. Our sun just didn't appear, poof. It actually was formed through a process. A beginning of a star is a nebula. It's a nursery, kind of like a preschool. These gigantic clouds that you see here, hundreds of light years across, okay, and they're made up of dust, a combination of dust and gases. And there you go, hydrogen and helium, the two main components, the two main elements, hydrogen and helium. Inside this nebula, inside this space that you see here, you are going to have the dust and the gases moving around, swirling around, mingling with each other, kind of like what we do at a party, right? We go in, or a school dance, we go in, we mingle with each other, okay? Sometimes a nebula can be disturbed by a galaxy collision, so colliding of gases and these, and this dust, and it can cause a nearby supernova explosion. When this happens, okay, then you've got the hydrogen gas and the dust, they begin to clump together, okay, and they start to spin. So now as they're clumping together, they're going to start making this motion of spinning, and they're going to collapse. And it's going to have a lot of weight and pressure. Now it's building, it's starting to form a core of this particular star. And again, you've got the forces of gravity just at that right time. Now you're going to get a spherical shape. And that doesn't take a week, a month, a day, or a month or a year. It can take billions and billions of years for this to happen. And it's constantly exploding. So here is an example of supernova. And also we're going to here's our field trip. We're going through an Orion Nebula at this moment where stars are constantly forming. Notice the gases, notice the floating particles, the dust, different colors. This one here is 2 million years old. So our sun is 4.6 billion years. And again, a lot of this imagery and video is captured by our technology, our telescopes. You guys know Hubble telescope. So that kind of gives you an idea of a nebula, a nursery, what's going on inside it with the dust and the gas particles mixing and mingling together. Here are 4 different images of what's called a protostar, which is where it combines together finally, and you have that gravitational force, okay? It takes on a different mass. It is a young star at this point in time, and it's still collecting dust and gas from its parent nebula, which is where it's gathering these things from the nursery. If you look up here in the 4 different pictures, here you've got one in 2000, okay? Again, taken from a different telescope, a different wavelength of light. You're going to see some changes. First of all, you see very brightly these two stars right here that have formed very close to each other. And then here's Spitzer, one of our telescopes, in 2004. So 4 years later, you see some change in just 4 years. You start to see maybe another star even out here next to it. Remember, stars can keep forming and even forming with each other next to each other and still playing and talking with each other, okay? So this happened right here. And then right next to it, another 5 years later, from 2004 to 2009, you've got what looks like kind of like a black hole. It also, a different mass of a star has maybe formed. But you can see here, it's still in the same, kind of like Rigel and Betelgeuse. They're still kind of in the same area from these pictures here, 9 years later. Still in the same area, but they're collecting more matter and they could become different size stars, different color stars. Oh, but then all of a sudden, where you see this black spot right here, guess what's forming? Yep, telescope Spitzer actually picked up in 2000, I think this is 2011 maybe, so maybe 2 years later. You've got that one star that looked like it was going to be a black hole, but it's not. It's actually another star, and it's forming right next to it. So once again, you've got some changes that are constantly happening with star formation. Okay, so a young star is formed. Now, after the protostar, you've got what's called a main sequence star. Our sun is a main sequence star. And it begins with that fusion. Well, not begins, but it continues. It's fusing hydrogen constantly, okay? And this time, this fusion is going to be the longest phase of a star's life. It'll be a main sequence star for a long time. How old is our sun? 4.6 billion years old. That's old. And that is where our sun is right now. It's an average yellow medium-sized star or a main sequence star. So it's going to continue this fusion process for a long time. So remember we said that the sun is at the center of the solar system, and when it starts to form itself as a protostar from the star nursery, the nebula, it can start to form, and then all of a sudden this gravity pulls down and then it starts to circle. So what happens with that remaining dust and gas? It kind of gets pushed out. If you notice here, you can see a star is born, and it's starting to circle around. And as you do that, kind of like you throw a rock in the water, it ripples out, right? So kind of like a star is born, that's your rock, and then all of a sudden it ripples out. And as it does that, that rippling effect is circling. So where do we get our planets? They get them from the star, from this extra gas and dust that is rippling away from this star formation. Okay, so it's a rotating cloud of gas, dust, and interstellar debris, that's basically the garbage, surrounding a developing star. So I believe that we are definitely made of star stuff. Because as you see, this is how a star is born. These are how planets, this formation and the leftover that's circling around the star is what has formed our solar system, our planets, our moons, okay? So yes, we're made of star stuff. So there are other types of stars. If you look in the sky, I mentioned there are red stars, there are blue stars, there are yellow stars, there are white stars, there are black holes. All of these types of stars are formed by one thing, the supernova explosion. So basically stars mingle with each other, but they don't fail, or they fail to make a star. Then they get upset and they re-explode. Okay, and then of course it affects other stars that are forming when you get stuff splattered on you, right? And it affects their formation. So for example, a good idea of this is you clean your room. Okay, your room is nice and clean. Put your shoes away, you put your books away, you make your bed, and then you leave your room to go to school, go play outside, and you come back inside, your room's a mess. How did that happen? Well, you could call it your dog came in and did it, or your little brother and sister did it. But in the star world, it's a supernova explosion. What once was something kind of neat and a star forming ends up being this huge, massive supernova because it didn't work out. Sometimes you have defective stars, okay? And those defective stars make a big mess, okay? So if you notice, different kinds of stars can form, okay? The different colors are different sizes, but heat and light. So you can measure it, being very hot or very cool stars. Here, of course, is formation of a star right here, and you can see the protoplanetary system, the disks that go around the star. And then, of course, you see small stars. This here is Orion. This is the constellation of Orion, and this is Orion's belt. So Betelgeuse and Rigel are a part of this constellation. And we're still looking out for a Betelgeuse and Orion to explode at some point. They may have already done that because it's light years away. But they're different colors. You can see different sizes, okay? Also, you have what's called a black hole, and a black hole has variant flow. It'll take in a lot of, it's like a vacuum in a way. It'll take the extra star stuff and then it kind of hogs it, it hoards it, and it takes it all and it starts to remix itself again. So it sucks all that in and starts to form something. It tries again after that explosion. So here you're going to see a supernova explosion. Notice the different, really, really big and bright, and now it's back down to nothing, but the leftover stuff is stretching out and even hindering different star formation, okay? So this can happen a lot, okay? So this is where we are led up to our life cycle of a star. So as you remember, we start in the nursery, the stellar nebula. Remember we kind of flew through it, little field trip? Now, the star nebula, different stars can begin their life from there, okay? As you notice, this average star, it sounds familiar. Well, that's our sun. We're the average medium star. So we formed from a stellar nebula, a nursery, and here we are as the sun. Or it could go the other way. It could be a very cold or cooler star, not as much mass, and it will become a massive star. Well, this massive star generally, not always, forms into this big red supergiant, okay? And that supergiant is, it's not as successful. So it was a cooler star. It's fusing, but it's not doing it well enough. And then it starts to just kind of, it starts to slowly explode from itself, which is where you saw that really bright light. And from that, you're going to cause the supernova explosion. So this is kind of like a failure of stars down here at the bottom. That's where you'll see your blue stars. And then, of course, they get really bright red after a while. And then, of course, that supernova explosion happens. And two things can be caused from that. So you can get a black hole from a supernova explosion, okay? It sucks all that material back in again and mingles, okay? Or you can get what's called a neutron star, okay? And that's going to be a very tiny star from where it was rather large as a supergiant. So this is kind of a failure of stars here, but a possibly re-beginning in two different ways. It could just be a black hole where it's just kind of constantly just taking things in, debris, gases, or it could actually form something very tiny as a neutron star. And those are the smallest ones in the sky with your telescope that you can see. Now, if it's successful, okay, you're going to have an average medium star like our sun. And after a while, our sun will become what's called a red giant at some point, okay? It'll still be billions of years from now. It's already 4.6 billion years old. It'll still be a while. And from there, guess what? It could form a planetary nebula. So the beginnings of another solar system. So our sun is giving us life and life to the planets. Okay. It'll become a red giant at some point. But from there, it could become the beginnings of another planetary system. Okay. And that's pretty cool that our sun is giving life to other solar systems. Okay. And or at some point, that white dwarf, so this planetary nebula from the outside, that rotating disk, white dwarfs can form within that planetary nebula. Okay. And that could send out these smaller white dwarf stars and to form those solar systems that we talk about. So it's a very cool process. But this here is a very successful star being born and being a part of our Milky Way galaxy. So how do we know all this? How do we know all this information of our sun? Well, we've had many different telescopes, even on the ground. In Chile, which is in South America, we have the Mauna Kea, which is in Hawaii. Those underground observatories from the Earth have been able to capture activity from the sun. It's a lot safer place, right? But we've also created some technology. And this technology is watching the Earth, watching the sun, then watching the play between the two. This is how we discovered the northern lights and the damage of the solar flares, where it's coming from. So the first one we have here is the Solar Dynamics Observatory. It helps us understand the influence of the sun, okay, on the Earth. And of course, nearby space, other planets like Mercury and Venus, okay, before us. It's studying the magnetic fields, which is how we know it's sporadic, okay, always. It can shoot out and cause solar flares, or it can cause those black sunspots, okay? It also looks at the magnetic energy, measures it, and the release of solar winds, which is what's taking the solar flares, those different colors, and that wind blows it out into the solar system, okay? We've got the Parker Solar Probe. This one is one of my favorites. It has been traveling through the sun's atmosphere. The Parker probe is so close to the sun. It is closer to the surface than any other spacecraft has ever come close to it. So it gets hot, very hot. It has a lot of radiation, a lot of issues and conditions. The solar flares, that's always a problem there, right? When you're that close to the sun. But it has provided us humans so much information about the sun. When you saw the sunspots and the solar flares, okay, that there was captured more than likely by the Parker probe. We have created that to withstand the heat from and the radiation from the sun. So yay for humans, right? The SOHO, which stands for the Solar and Heliospheric Observatory. Remember how we opened up the sun to look inside? Well, the SOHO studies the internal core, the structure of the sun. It also does the same thing as the Parker probe. It does the external, the outside part. And then, of course, what causes the solar wind? So we kind of know it's a little bit of fusion, right? And the flares being sent out. So it does both inside, outside of our sun. Here we have the Henode, the Japanese, how do you say it? Like NASA, we have JAXA in Japan. So they created the Henode Solar Observatory. So an observatory, just like the SOHO, it's an observatory also. It has different instruments on board. So it has a telescope, it has an X-ray telescope, it has the spectrometer, which is a measure of gases that are present in the Earth's atmosphere, but also kind of controlling and measuring the amount of helium and hydrogen in our sun. So it has those science instruments on board, just like the SOHO does, okay? And this is where you get the different colors of video or pictures is from this right here. It changes the color to see different things inside. X-rays tell you one thing, gamma rays tell you another thing because they use the electromagnetic spectrum that tells you different colors, okay? So remember I told you about the northern lights? Well, those gases present in our atmosphere turn it different colors, and that is because of the solar flares that have been sent out by the wind, the solar wind in the space from the sun, and we get the North Pole and the South Pole experience these northern lights. So it's beautiful imagery of the northern lights. So I hope that you enjoy.
Also known as the northern lights, auroras are the brilliant curtains of colored light that appear in the night sky in the far northern or southern regions of the world. Although auroras are spectacular to watch, they're actually a manifestation of violent space weather.
These are just caused by energy coming into our Earth's magnetic atmosphere, causing the whole magnetic field to reconfigure and end up with an explosive release of high-energy electrons and protons into our Earth's atmosphere, where they strike the molecules, both oxygen and nitrogen, and cause them to glow.
Different colors are different gases in our atmosphere.
Besides igniting the northern lights, these substorms can create big problems here on Earth by disrupting power grids, satellites, air travel, and even GPS signals. Spring is one of the best times to view the auroras because the substorms that spark them are more frequent in the months around the equinoxes. Plus, the longer nights provide a great backdrop for these stunning displays. While auroras have fascinated observers for centuries, little had been known about their origin. But NASA's aiming to resolve this mystery with a new mission to study the northern lights called Themis. The Themis mission uses 5 identical satellites and a network of ground observatories to track and determine what triggers the auroras that occur during substorms. And since its launch just last year, Themis has made some important discoveries.
Even in the first days of our mission, we've used the 5 spacecraft and the dedicated array of ground observatories to track aurora racing westward across Canada and Alaska and time their motion and understand where they occur.
As our knowledge about the northern lights continues to expand, pretty soon, auroras may not seem so mysterious after all.
So I like to just kind of point this out here. The coloring, it looks like our planet's on fire. In the North Pole, doesn't it? And in the South Pole. But when in fact, you know that the Earth is tilted, okay? And then it rotates on its axis. It goes around on its own, okay? It gets very dizzy is what I call it. So it looks like it's on fire, but it's not. It's solar radiation that has been sent out different times of the year when in the fall, and like your August, September, October months. And of course, in the springtime, when you have March, April into May, you're going to see the northern lights a little bit better. When you shine a flashlight out in the middle of the day, can you see the light much? No. Why? Because we already have sunlight coming down, it kind of blocks it, right? But if it's dark outside, okay, you use your flashlight so you can see it. So the best time to see the northern lights will be at night. And of course, the best time to witness the different colors is at night, because you can definitely see light regardless of the color on a black night where it's dark. And that is when you can notice here, that is when they've come up with the best images of the northern lights right here. And again, they're called auroras. You guys, if you know auroras or northern lights, and yeah, you can see here's China right here. So I'm sure you guys get the opportunity to witness some northern light activity up in this area, and it stretches all the way around the Arctic Circle. Okay, so you'll see some in America, but it won't be until it's dark. Because remember, we're now 13 hours apart from each other. Where I am at what, 6:52. So I think you guys are like after 8 o'clock at night. But this again is the best time to see it right here, is at nighttime and more or less in the fall into winter time, because you won't be able to see as much in the springtime or very early on in the springtime. when it's still dark. We haven't sprung ahead in time yet. So, and again, down here, but not many people live down here in the South Pole. It's much too cold, but definitely pay attention to the North Pole activity there in China. All right, so this, just other than just seeing some resources, I wanted to show you. Boys and girls, I worked at the Space and Rocket Center down in Huntsville, Alabama. So a lot of my information has been collected over years of giving presentations to kids all over the world. But I have also used Ivy's Big Universe, lots and lots of information here. You notice the Lexile level. So you can have be a first grader and learn about the sun. You can be a 12th grader and still learn about the sun. So it definitely is a different span. This one here, pretty much anyone can read this book. Very easy to read, very good information. And then you've got your stars. It talks about how stars are born, and you should know now, okay, from nuclear fusion, from a nursery, and they can go two different ways, successful and a failure. Here is a book about the sun itself, okay, how it was formed. And you've got the sun. This one's a little bit more technology. You can notice here you've got some kind of looks like little technology science instruments up here at the top. So it's going to talk about some technology in this book, like the Soho and the Henode from JAXA, from the Japanese Space Agency. It'll talk about them. Space, okay, this is a 930 Lexile, so you're getting up into middle high school, but it does give you good information. And you notice here, this looks like a planetary disk that's being formed from the star in the middle. And you have the swirling activity that goes on here. So once again, amazing. These are just 5 books that I pulled. I used more than 5 books, but these are some of my favorites. So please make sure you check out Big Universe. Log in. If you don't have a login, let your Ivy admin know that you'd like to get access to Big Universe to study the sun and the stars. Well, guys, thank you very much. Our time is over, and I would like to encourage you guys to study on and ask lots of questions. So I'm going to come back over here, and the floor is yours to ask me any kinds of questions.
Well, I didn't see anyone want to ask a question. So do you have anything more you can show them?
Not at the time, but I definitely want them to go to Big Universe and check out some books that I used. I showed them just the 5 that I was able to have room for, but definitely something that they could do on their own time and at their own level of reading too, to kind of study further.
Okay, thank you.
You're welcome. All right, guys. Well, I did like this one here. The Orion Nebula isn't hundreds of light years. It's only 3 light years. Yeah, so that was a field trip we went through. So definitely good information on this. All right, guys. Well, good luck out there, and I'll see you later. Bye.